What's up, algebros and broettes? We're doing math on the internet, so don't adjust your TV sets. Let's get linear. Hey, hopefully you're here excited to talk about determinants, because that's what we're talking about today. So let's talk about computing the determinant of a matrix. And there's some very nice textbook definitions here. Let's read through them. This is a safe space, so it looks scary. For n greater than or equal to 2, the determinant of an n by n matrix A, here we talk about the entries as being little a sub ij, where I is talking about a row position, j is talking about a column position, is the sum of the n terms of the form plus or minus little a sub ij times the determinant of big A sub ij, with plus and minus signs alternating, where the entries little a sub 1, 1, little a sub 1, 2, little a sub 1, 3, so on and so forth, little a sub 1, n, are from the first row of A. Symbolically, the determinant of matrix big A looks as follows. We have little a sub 1, 1, determinant of big A sub 1, 1, minus little a sub 1, 2, determinant of big A sub 1, 2, plus little a sub 1, 3, determinant of big A sub 1, 3, minus, so on and so forth, plus, we get to the end. We don't know if it's a minus or a plus sign. That depends on what n is. We could say in a closed form, that's negative 1 to the power of 1 plus n times little a sub 1n, determinant of big A sub 1n. Or we could write this in a closed form with our capital sigma notation. That is the sum from j equals 1 to n of negative 1 to the power of 1 plus j, and then little a sub ij, determinant of big A sub ij. Right? And we have a theorem to help us out with this. It says the determinant of an n by n matrix A can be computed by a cofactor expansion across any row or down any column. And this is actually very important. You're going to hear me say this over and over again. We can do a cofactor expansion across any row from left to right. Any row you like from left to right. Or you can do it down any column, top to bottom. Any column from top to bottom. So you get to choose the row or the column that you want your cofactor expansion to be done about. And the expansion across the ith row using the cofactors is given as follows. Determinant of big A is little a sub I1 C for cofactor of I1 plus little a sub I2 big C I2 plus so on and so forth. We get to the end plus little a sub IN and then big C sub IN. And then the cofactor expansion down the jth column, trying to keep things general here, would be determinant of matrix capital A is little a sub 1j and then capital C sub 1j plus little a sub 2j, capital C sub 2j plus so on and so forth. We get to the end, we're adding plus little a sub nj, capital C sub nj. Now, all of this information is great. Sounds like it's coming directly from a textbook. But we're going to talk about how to actually compute these. It's not going to be so bad, I promise. Not going to be so bad. But some important things that I want you to remember of all of the things I just said is that we can choose how to do a cofactor expansion. It can be across any row from left to right or down any column from top to bottom. But one other thing that I need to talk about before we jump into computing determinants is the checkerboard pattern. And this is a bit of a behind the scenes when doing a cofactor expansion. Now, checkerboard pattern, we call it this because it looks sort of reminiscent of a chessboard or a checkerboard. But if I have, let's say, a 3 by 3 matrix, not only do I have the entries in the 3 by 3 matrix, but there's an alternating plus or minus sign that's going on as well. So in the upper left corner, we would have a plus, and then from there it alternates. So then if I'm going across the row, it would be plus, and then minus, and then plus. If I go down the column, it would start at that plus, and then it would be minus, and then plus. And I can fill in the rest accordingly. So the second row would be minus, and then plus in the middle, and then minus. And then the third row would be starting at plus, and then minus, and then plus. And it would continue this for larger square matrices. We only find determinants of square matrices. So 3 by 3 and then 4 by 4, for example, we can talk about. And it's that same alternating plus minus sign checkerboard pattern. So for a 4 by 4 matrix, here in the upper left, it would be plus, and if I want to go across that row, it would start at plus and then minus, plus, minus. Second row would be minus, plus, minus, plus. Third row would be plus, minus, plus, minus. Fourth row would be minus, plus, minus, plus. Now, this, and I want you to listen to me very carefully, I want you to listen to what I'm going to say. This is not trying to tell me that the entries that live in any specific spot of the matrix are supposed to be positive or supposed to be negative. What this is trying to tell me is when I bring a term out to build a cofactor expansion, I'm either going to keep the sign as it is or change the sign of that number. So we think of it like either multiplying by a positive 1 if there's a plus, or multiplying by a negative 1 if there's a minus. So it's either going to keep the sign or flip the sign. But it's not trying to tell me if the number should be positive or if the number should be negative. It's not doing that. So for example, if I had, let's say the number I had in this upper left corner of a 3 by 3 matrix was a 7. I would keep it as a positive 7 when I bring it out of the cofactor expansion, because the plus sign means don't change the sign. It means multiply by a positive 1, which does nothing. Whereas, let's say I was doing a cofactor expansion here in the second column, and I was using this first term in the second column, there's a minus sign associated with that entry. Let's say that this entry was a 4. If I bring this 4 out, I would have to flip its sign. The minus sign there is telling me multiply by a negative 1. Flip its sign. If it's positive, make it negative. If it were negative, make it positive, right? So the plus signs, whenever I bring out a term that's sitting where a plus sign would be behind the scenes, and remember, no one's going to tell us if there's a plus or a minus sign associated with the entry. We are responsible for this. We have to remember this. We have to know this. But if I pull out a term that's associated with a plus sign, don't change it. If it's positive, leave it positive. If it's negative, leave it negative. However, if it's associated with a minus sign, we have to flip the sign. So if I was doing a cofactor expansion, let's say across the second row, and I started with a first term here, let's say that first term was a negative 2, when I bring out that negative 2, since it's associated with a minus sign, I would have to flip it to a minus negative 2, or that would be now a positive 2. Remember that. Keep in mind, depending on where we are, we're either going to keep the sign the way it is, positive stays positive, negative stays negative, or we're going to flip the sign. Positive becomes negative, negative becomes positive. But we have to remember that. That's on us. I got to remember that. But aside from that, remembering that we have freedom for our cofactor expansion and how the checkerboard pattern looks, we should be able to do this. And the idea is to break down to smaller square matrices to eventually get to a point where we can talk about 2 by 2 determinants, which we know how to find the determinant of a 2 by 2 matrix. Let's refresh. If I have a 2 by 2 matrix with a first row AB and a second row CD, the determinant of that 2 by 2 matrix, I multiply on the main diagonal, that's A times D, and I subtract the product on the off diagonal, so minus B times C. So we can do a 2 by 2 determinant no problem. But let's take a look at a 3 by 3 example. Remember the checkerboard pattern. Don't you dare forget it. But let's talk about this first example. I want to find the determinant of the following matrix, and let's do this 2 different ways so that you can see that we have this freedom. Let's start with a cofactor expansion along the top row. Now, when I bring this 3 out, it's associated with a plus sign. Remember how that checkerboard pattern looks? I can jot it down real quick. Before I start doing this, let me just mention for anyone already commenting in the comment section below that you don't have to think of it as a checkerboard pattern. There's a bit of a more mathematical way to think about it. When you bring a term out, you could say that you're multiplying by negative 1 to the power of I plus j. Well, actually, let me do, I think, maybe a bit of a more, this is a fine notation. I think it coincides nicely with what we were saying. It doesn't really matter what you call these, but another common way to write it is negative 1 to the m plus n, where m refers to the row position, and n refers to the column position. So for example, right here in the middle, if I want to sort of check this, we'd say, well, where is that? That is in the second column, second row. So if I bring that term out, I would multiply by -1 to the 2 plus 2, or that's -1 to the 4, which is positive. Shows me that positive sign there. But what if I was at this entry here? I can see that it's got that minus sign from my checkerboard pattern, but if I didn't know this, or if I wanted to do it this way, I'd say, well, this is in the third column, second row, so the row value is 2, and the column value is 3, so it would multiply by a -1 to the 2 plus 3, -1 to the 5th, which is -1, so it stays negative. Just another way to think about it, a much more mathematical way to think about it. But I like the checkerboard pattern. So I'll say, okay, when I find this determinant, I can start by bringing out this 3, and I'm just going to go across the top row, from left to right, 3, 0, 4. When I bring out this 3, it's associated with a plus sign, so I don't flip its sign. I keep it as a 3. So I'll name this A, and we'll say the determinant of A. When I bring out that 3, I now have to multiply this by the smaller 2 by 2 matrix that I get when I remove this entry's row and column. So this is sort of the trick, and we get used to doing this. So if this is your first time computing a determinant, it might seem a bit weird. When I bring out this 3, I bring it out. Since it's associated with a plus sign, I don't flip its sign. But now I want to think about going to this 3 and eliminating the row and the column that it lives in. And I would just cross it out, but I have to use this matrix for some more work. But the idea is I would just sort of, think about this row being gone and this column being gone. And what does it leave me with? It leaves me with this smaller 2 by 2 matrix here in the sort of the bottom right. So then times the determinant of, here I have 3, 2, 5, -1. And what I like to do, if I'm actually doing this with, pen or pencil, I would maybe take like 2 pens, and I would kind of crosshair it to sort of, right there where that entry is, so that I can kind of cover it up. So I'm only looking at what I want to write for the remaining matrix. And then we would continue. So now I would bring out the 0. It's associated with a minus sign, so say -0, and then times the determinant of the 2 by 2 matrix that I get when I remove that entry's row and column. So go here to the 0, remove the row that it's in, remove the column that it's in, think about crossing it out, and I have to sort of jump around, but I'm left with 2, 2, 0, -1. I think it helps to sort of cover it up with a couple of pencils, if you got a couple pencils. And then now I'm almost done. Now I got to bring out this 4. The 4 is associated with a plus sign, so I don't have to flip its sign. So I just bring it out as a +4 times the determinant of the 2 by 2 matrix that I get when I remove that entry's row and column. So go to the 4, get rid of it, and here I can sort of show you what I mean. If I cross that row out, cross that column out, that's what I end up with. And now I have this remaining 2 by 2 matrix. I can sort of see 2, 3, 0, 5. And now I compute this as a linear combination of 2 by 2 determinants. So I should be able to go through the rest of the work because I know how to find these smaller determinants. So I'll say, well, what is this going to give me? Well, here I have 3 times, here if I do the 2 by 2 determinant, 3 times -1 gives me -3, minus 2 times 5 is 10. And then here I have this 0 times whatever this is. I don't really care because I'm multiplying it by a 0. So I'm just going to write -0 there. Zeros are nice, so you can sort of skip over that one. And then plus here I have 4 times. And then here for the 2 by 2 determinant, I get 2 times 5 is 10, minus 3 times 0 is 0. And I should be able to go the rest of the way with this. So what am I left with? I'm left with 3 times -3 minus 10. I don't need the 0. It's not going to do anything. And then plus 4 times 10 minus 0 is 10. And you could go ahead and you could do more arithmetic than I've done, but I'm actually going to start distributing. I think it's going to be easier to compute that way. 3 times -3 is going to give me -9. And then minus 30, I'm distributing in. And then plus 4 times 10, so that's plus 40. It doesn't look so bad, right? 40 minus 30 gives me 10. Minus 9 gives me 1. So the determinant of this matrix is 1. But what I want to stress here is that I just did a classic cofactor expansion across the top row. You don't have to do that. You can pick any row or any column. And just to show that that's the case, let's rewrite the matrix. Let me get a different color because we're going to do this a different way. I like the baby blue. Let me know in the comment section what your favorite secondary color is. I don't mean that in terms of literal secondary colors. I like to use the yellow because it reminds me of chalk, like I'm in the classroom hanging out with all y'all. So I'm usually with the yellow, right? You see me, I'm using the yellow a lot. But then I got these other colors. What do I got? I got a really nice kind of neon purple, got a neon pink, got a cobalt blue, I got green. Green means go. I got the yellow, which we talked about, and I got red. Red means don't go. Don't go. 0, 5, -1. So let me know what color you like. I can try to work it in. I try to use them a bit. So this is the original matrix. Let's do a different cofactor expansion. What about down the second column? So we did across the top row. Let's go down the second column. So remember that checkerboard pattern, plus, minus. When I bring out this 0, I'm going to bring it out with the minus sign. So that's -0 times the determinant of the 2 by 2 matrix that I get when I remove its row and column. So go to the 0, get rid of its row, get rid of its column. So that's 2, 2, 0, -1. And then I'm going to go down to this 3 in the middle. And that's plus, minus, plus. So that's a plus sign associated with it. So I don't flip its sign. I keep it the way it is, plus 3. Times the determinant of the 2 by 2 matrix that I get when I remove its row and column. So that's kind of the corners, right? 3, 4, 0, -1. And then lastly, so plus, minus, I bring out the 5, but I got to flip its sign, so it's positive, so I make it negative. If it were negative, I would make it positive. But that's not the case. Times the determinant of the 2 by 2 matrix that I get when I remove its row and column. So think about just sort of crossing out the row and column that 5 lives in. I'm left with 3, 4, 2, 2. And now I compute the smaller 2 by 2 determinant. Here where I have the 0 right in front, it doesn't matter what this is. I'm going to multiply it by 0 anyway, so that's gone. Then I have plus 3 times. I have 3 times -1 is -3, minus 4 times 0 is 0. And here I have minus 5 times. Here 3 times 2 gives me 6, minus 4 times 2 is 8. We can go through the rest of the arithmetic. So here I have 3 times -3, minus 5 times -2, and this is -9 plus 10, gives me 1. And that should be familiar. It shouldn't give me a different answer. It's just a different way to compute the determinant. And I can go across any row from left to right, or down any column from top to bottom. So you have that freedom. Let's take a look at another example. Let's do this one in 2 different ways as well. I'm a big fan of that traditional cofactor expansion across the top row. If I can't see any advantage to doing something differently, I would just do that. And if you've already taken Calc 3, then you've likely done this a lot with cross products anyways, so it might be familiar and comfortable for you. Let me go ahead and go across this top row. Remember the checkerboard pattern, don't be ashamed to write it down. So when I bring out, so I'm going to cross this top row, 2, -4, 3 is what I'm going to do. When I bring out the 2, I'm not going to change its sign. And then times the determinant of, if I go to that entry, remove its row and column, I'm left with 1, 2, 4, -1. And then I'm going to bring out this -4 along this top row. But here it's associated with a minus sign, so I have to flip the sign of that value. So it's already negative, so I'm going to have to make it positive, right? So plus 4 times the determinant of the 2 by 2 matrix when I remove that entry's row and column. So that's 3, 2, 1, -1. And then now I'm going to bring out this 3 at the end of that top row. It's associated with a plus sign, so I'm not going to flip its sign. I'm going to keep it the way it is. It's perfect. That's going to leave me with 3, 1, 1, 4. And now I compute the 2 by 2 determinants. So 2 times, here I have -1 minus 8, plus 4 times, 3 times -1 is -3, and then minus 2 times 1. And then 3 times, here we have 3 times 4 is 12, minus 1 times 1 is 1. And let's see where we can go with this. So here I have 2 times, this is -9, plus, whoops. Every once in a while I get a cool stray stylus mark. I like to delete that for you because you're worth it. 4 times, this is what, -5. And then 3 times 12 minus 1 is 11. Let's see what we get. So here we have -18 minus 20 plus 33. I'm going to start here, right? 33 minus 20, that's going to give me 13. So -18 plus 13 is going to give me negative 5. But we're saying that we can do this cofactor expansion really however we'd like. It doesn't have to be across the top row. It can be across any row, or it can be down any column. So let's take a look at what do you want to do? I mean, you're not here with me, so I can't really take your advice. But let's take a look at what if we just did a cofactor expansion down the first row, or down the first column. Let's do down the first column. So let me rewrite the matrix just for reference. And it doesn't matter. Pick a different row, pick a different column, and let's race. I'm going to go down the first column. I'm going to bring out this 2. Remember the checkerboard pattern? I got to bring it out as the way it is, multiplied by a positive 1, times the determinant of the 2 by 2 matrix when I remove its row and column. So that's 1, 2, 4, negative 1. And then I'm going to bring out the 3 here underneath it, but I have to flip its sign. It's positive now, so I make it negative, times the determinant of the 2 by 2 matrix when I remove that entry's row and column. So that gives me negative 4, 3, and then 4, negative 1. So plus, minus, and then plus. So now I'm going to bring out this 1 at the bottom of the first column, and I keep it the way it is. I don't flip its sign, so it's positive 1 now, and it's going to stay positive 1. Times the determinant of the 2 by 2 matrix when I remove that entry's row and column. So this is the entry I pulled out, remove the row that it lives in, remove the column that it lives in, and I'm left with negative 4, 3, 1, 2. I can see that. I can see the entries. And now we can compute the 2 by 2 determinants. So we just compute the rest. So I have 2 times, here we're going to get negative 1 minus 8. And then minus 3 times, here I'm going to get positive 4 minus 12. And then plus 1 times, here I'm going to have negative 8 minus 3. Let's see what we get. Hopefully nothing different. So we get 2 times negative 9, minus 3 times 4 minus 12 is negative 8, plus, and then here, negative 8 minus 3 is going to give me negative 11. And let's see. So we have negative 18, and then here this is going to give me plus 24, minus 11. And I can go ahead and, work through some of the arithmetic. So I have negative 18, and then 24 minus 11 is going to give me plus 13. Looks familiar. It's going to give me that negative 5 again. Just a different way. So you have a lot of control over how you do that cofactor expansion. So you can kind of make it your own a bit. That's not going to give you a different answer. Let me know in the comment section if you did a different row or a different column, and let me know what you got. But I think I got a good idea as to what you probably got. Now with this in mind, we have control over how we do the cofactor expansion. So you can choose whatever you'd like to. So here I have this matrix. I want to find the determinant of it. There's a big incentive to want to do something that's going to maybe make a little bit less work. Now, truth be told, if I'm utilizing a 0 directly, that's good. If I'm not utilizing it directly, then it is going to show up somewhere else in my work, so it's going to help out anyways. But if I want to try to get any 0 entries to help out the most, I want to try to consider them in my cofactor expansion. So I look at this matrix here. I say, well, if I'm just allowed to find the determinant how I see fit, I would either want to use the second column or the second row, because the 0 is in the second row and the second column. And that's going to kill off part of my cofactor expansion and make it a bit faster. So if I'm going down the second column, remember that checkerboard pattern, plus, minus, I'm going to bring out that 3, I'm going to flip its sign, and then times the determinant of the 2 by 2 matrix that I get when I remove that entry's row and column. So that's 4, 5, 5, 6. Next, I'm going to bring out the 0, I'm going to keep its sign, and then times the determinant of the 2 by 2 matrix that I get when I remove that entry's row and column. So that's 2, negative 4, 5, 6. But I don't really care about this one because I know I'm going to multiply it by a 0 anyways, and it's going to kill off that term. So that's why I'm choosing this. So plus, minus, plus, minus. Now I got to bring out the 1, but I have to flip its sign to a negative 1. Times the determinant of the 2 by 2 matrix that I get when I remove the entry's row and column. So that's 2, negative 4, 4, 5. And now I can compute the determinant. So here I have negative 3 times, here 4 times 6 is going to give me 24, minus 5 times 5 is 25, plus this 0 that I picked on, it's just going to give me 0. I don't care what the determinant here is. I'm going to multiply it by 0 anyways. And then minus 1 times here, 2 times 5 gives me 10. And then minus negative 16. So here what do I wind up with? I have negative 3 times, this is a negative 1, and then plus 0, and then minus 1 times, this is really 10 plus 16 gives me 26. So going through with this here, I have negative times negative is positive, so that's 3, and then minus 26, which is going to give me negative 23. And you can choose how to do that cofactor expansion. I chose to use a 0 because it made things a little bit easier computationally. But now we can talk about these examples where we're going to want to find the determinant for the matrix. We're going to try to do this using the least amount of computation possible. So we'll say, well, how can I go ahead and do this? This is where we're saying utilize zeros. Right, so when I'm looking at this, I want to first get sort of a survey of the matrix and try to get an idea as to what's going to be the easiest for me. Okay, well, if I look at where the most zeros are, it's going to be here in this third row. Right, I have a lot of zeros, only one non-zero entry. Let's use that. So think about that checkerboard pattern. That's plus, minus, plus. When I bring out that 2, I'm bringing it out the way it is, and then times the determinant of the 3 by 3 matrix that I get when I remove the entries row and column. Now, I can write the rest of this cofactor expansion, but it's going to be, minus 0 times some determinant, and then plus 0 times some determinant, and then minus 0 times some determinant. And since I'm multiplying all of those by zeros, they're not going to be of any consequence to me. So I choose this because it really just gives me one usable term. And when I remove the entry, that's this 2, I sort of crosshair it here. When I remove its row and column, I'm left with a 3 by 3 matrix, 0, 0, 5, 7, 2, negative 5, 3, 1, 8. Well now, and then the rest of these are just zeros. But now focusing on this piece here, what I want to do is I want to do this process again. Now whenever I build this smaller matrix, think about it like almost resetting the problem. The checkerboard pattern resets as well. So I'm no longer thinking about the original checkerboard pattern of the 4 by 4. I'm now resetting to a checkerboard pattern of the 3 by 3. So we start fresh with this in some regards. So now we say, well, let's go across the top row. The top row has the most zeros. So I still have this 2 in front. I'm babysitting it. But then here I'm going plus, minus, plus. So I bring out the 5. I don't flip its sign. And then times the determinant of the 2 by 2 matrix that I get when I remove that entries row and column. And that leaves me with 7, 2, 3, 1. And now I just compute this directly. So here I have this 2 times 5. And then here 7 times 1 is 7. Minus 2 times 3 is 6. We'll say, well, what is this going to give me? 2 times 5 is 10. 7 minus 6. I want to do this sort of bracketed away from the others. 7 minus 6 is 1, so this is going to give me 10 times 1 is 10. Now, I could have done this a very different way and still got the same answer, but it would have likely been more work, more computation. Now, let's take a look at another example, practicing finding the determinant using the least computation. So if I'm looking here, if I want to utilize the most zeros, I would say, okay, well, going down this first column would be great, because I only have one non-zero term. So here, if I go ahead and pick out this 3, remember checkerboard pattern means it's associated with a plus sign, so I keep the sign, keep it the way it is. Right now it's a positive 3, times the determinant of the 3 by 3 matrix that I get when I remove the entries row and column. Keep in mind, though, the rest of this is just going to be zeros, right? Minus 0 times the determinant, plus 0 times the determinant, minus 0 times the determinant. And I don't care about that because it's not going to give me anything that I have to actually compute. So sort of crosshair it, and then I'm left with this 3 by 3 matrix. I don't even, this stuff all here, this is all 0. Don't even care about it. Don't even look at it. Keep your eyes on the prize. We reset our checkerboard pattern. We do this again. The least amount of computation, and you could do this, bottom row. I'm going to stick with my first column though. So I have 3. Now I'm going to bring out this negative 2. It's associated with the plus sign, so don't flip the sign. leave it the way it is. It's a -2. I'm going to keep it negative, stay negative. Times the determinant of the 2 by 2 matrix that I get when I remove the entries row and column. So that's 1502. And now I can compute the 2 by 2 determinant. So here I have 3 times -2 times, here this is going to give me 1 times 2, and then minus 5 times 0. Let me actually write this out as a product first, and then we'll compute it. So this is 3 from the first cofactor expansion, then minus 2 from the second cofactor expansion. 5 times 0 is 0, and I'm left with 1 times 2 here. So this is what I wind up with if I want to write this out in terms of the factors. Now, certainly if I multiply it, I can get the answer. 3 times -2 is -6, times 1 is -6, times 2 is -12. So there's my determinant. But what do you notice about this? Let's go back to the original matrix. I sort of crossed out a bunch of stuff, but let me erase those marks that I made. It would be good to notice something about this. 3 times -2 times 1 times 2. And maybe you see this a bit in the mechanics of what had happened. But it's these entries along the main diagonal. Now what we actually have here, and we'll take a look at a theorem in just a bit, is a triangular matrix. This in particular is an upper triangular matrix. For a triangular matrix, we would say whatever happens on the main diagonal is fine. These can be either 0 or non-zero entries, but either underneath or above the main diagonal, everything has to be a 0. And if that's the case, we have either an upper triangular or a lower triangular matrix. I like to think of it this way. It's a triangular matrix if you can find the hidden slice of pizza. So there's my hidden slice of pizza with those pepperoni pizza with those pepperonis. The zeros are the pepperonis. So there's that slice of pizza. And this is referred to as, this one in particular is an upper triangular matrix. We designate whether or not it's an upper or a lower triangular matrix based on where the non-zero entries are. Here the non-zero entries are above the diagonal. So this is upper triangular, and the pizza slice is sort of lower, if that makes sense. And if just for the sake of talking, if we want to talk about how a lower triangular matrix would look, let's just we'll do another 4 by 4. And it doesn't matter, I can go ahead and pick whatever numbers. Let's say the main diagonal is 1, 2, 3, 4. If I want lower triangular, that means the stuff underneath the main diagonal have to be non-zero entries. Or they can really be anything, actually. They could be 0 as well, some of them at least, or all of them. But let's sort of stick with something that I think makes a bit more sense to show what I'm trying to show. So let's do -1, let's do 7, let's do 2, let's do, you like 8, you like -9, you like -5. And this is lower triangular, and everything above that main diagonal has to be a 0. Kind of looks a little jumbled together, but this here would be what's referred to as a lower triangular matrix. Because the zeros are above, the non-zeros are below. But it's really about being able to find this pocket of zeros, more so than the other entries. I don't want to give the wrong idea that I couldn't have some zeros hiding out in here. It would still be considered lower triangular because I have this pizza slice of zeros above the main diagonal. That New York City slice. Get sort of the gooey cheese on there. Do you like pizza? Let me know in the comment section. Let me know in the comment section below if you like pizza. So we were talking about triangular matrices. And if I have a triangular matrix, the determinant is going to be the product of the entries on the main diagonal. Hey, we got a theorem for it. If the matrix A is a triangular matrix, then the determinant of A is the product of the entries on the main diagonal of A, which is what we just saw in this example. All right, we're good for it. Take a deep breath, get that slice of pizza if you got it, and let's find the determinant of this. What is this, a 5 by 5? Kind of scary, but let's do it. Let's try to use the least amount of computation. I already can sort of spot it. It looks like the second row or the second column is going to be my best bet. Let me use the second column here. Checkerboard pattern, plus, minus, plus, minus. I bring out the 3, I have to flip its sign. If it were negative, I would make it positive. Since it's positive, I'm going to make it negative. So bring out that negative 3 times the determinant of the 4 by 4 matrix that we get when we remove that entries row and column. Now, I know that there's other parts of the cofactor expansion, but all of them involve zeros. So I don't even care about them. We skip over them. That's the point of doing this the fastest way with the least amount of computation. The remaining 4 by 4 matrix is 4, negative 7, 3, negative 5. We have 0, 2, 0, 0. We have 5, 5, 2, negative 3. And we have 0, 9, negative 1, 2. Striding out the rest of the entries into a 4 by 4 matrix. Now the checkerboard pattern resets. The process starts anew. And I want to do this again. Now, whatever I didn't do last time is now what I want to do this time, because now it's this second row here that's going to be the best. So the negative 3 is still there. When I bring out this 2, I got to keep them on my checkerboard pattern. Let's travel to it. Plus, minus, plus. I bring out the 2 as a positive 2. Well, I leave the sign alone is what I mean. Times the determinant of the 3 by 3 matrix that I get when I remove that entries row and column. So I can sort of cross it out now since I'm going to be done with this. And that's 4, 3, negative 5 for the top row. I skip over, and then 5, 2, negative 3 for the next row. Last row looks like it's going to be 0, negative 1, 2. Now, if I'm still trying to do this with the least amount of computation, that first column, down the first column looks good because I can use that 0. Across the third row is also a great idea. Let me go down this first column. So I have negative 3, 2, still babysitting that. When I bring out the 4, that's a plus, so I keep the sign the way it is. But be careful here. These things should be multiplied into what I'm doing now, so I'm going to use some parentheses. So it's going to be 4 times the determinant of the 2 by 2 matrix when I remove that entries row and column. That's 2, negative 3, negative 1, 2. And then I bring out the 5, I got to flip its sign. So negative 5 times the determinant of the 2 by 2 matrix when I remove the entries row and column. And that's 3, negative 5, negative 1, 2. And then the rest was a 0, so plus 0 times whatever. No consequence to me. And I really want to work inside the brackets here first, and then worry about this stuff in front later. That's negative 3 times 2. And then here I have 4 times, 2 times 2 is 4, minus negative 3 times negative 1 is 3. And then minus 5 times 3 times 2 is 6, minus negative 5 times negative 1 is 5, and then plus 0 there. And then not so bad, we can finish this off. So I have negative 3 times 2, which I'm still waiting on, or you can multiply that bit, only that bit so far. And this gives me in the brackets 4 times 1, minus 5 times 1. And that 0 I don't need. So negative 3 times 2, and then here I have 4 minus 5. So this is going to give me negative 3 times 2 times negative 1. So okay, well now I'll multiply. So here's going to give me positive product overall. 3 times 2 times 1 gives me 6. We should get positive 6. So not so a 5 by 5 seems scary, but it wasn't the end of the world, and we did it. We did it together. But the key is trying to make it the easiest on yourself. Now, I'd like to show you a trick for computing 3 by 3 determinants. Cofactor expansion is really where it's at. So do a cofactor expansion, but if you're sort of like, trying to do a cool parlor trick, or if you like magic, if you enjoy video games, this can be thought of similar to those. And this is a trick only for 3 by 3 matrices. Don't use it for a 4 by 4. Don't use it for a 5 by 5. Don't use it for a 2 by 2. Don't use it for anything else. Only 3 by 3s. But I want to show you this trick. And it says that we're going to add the downward diagonal products and subtract the upward diagonal products. But let's talk about this. What am I going to do? I'm going to rewrite the matrix. And I haven't closed it off yet because what I'm going to do is I'm going to rewrite the first 2 columns again. So 3, 2, 0 is my first column. Write it again. Second column is 0, 3, 5. Write it again at the end, just like I'm doing. And then now you can sort of close it off. Now, I like to think about this as a very boring word search with numbers, because now I'm going to find the downward products and the upward products. We want to go diagonally. So for downward, I'm going to start here at the upper left, and I'm just going to circle diagonally downward. That's 3 times 3 times -1, multiply. 3 times 3 times -1 gives me -9, but there's more of these. Next, I can move over. The next downward diagonal product, I'm circling it, is 0, 2, 0. If I multiply 0 times 2 times 0 gives me 0. And there's one more that I can find before I run out of space. And that's this 4, 2, 5. If I multiply 4 times 2 times 5, it gives me 40. Let's find the upward diagonal products in a very similar way. Only now I'm going to start bottom left and circle upward diagonally. 0 times 3 times 4 gives me 0. Let's move along. 5, 2, 3. If I multiply 5 times 2 times 3 gives me 30. And there's one more upward, sort of like a word search, right? One more upward product I can find. -1 times 2 times 0 gives me 0. And we want to add the downward, subtract the upward. So I take these downward ones, I add them together. So that's -9 plus 0 plus 40. And I subtract these upward products. So that's -0, -30, -0, subtracting these. Let's see what we get. So here, if I'm looking around, I got a lot of zeros that I didn't need to write. But 40 minus 30 gives me 10. So I have -9 plus 10 is going to give me 1. And it's just another way that I can find the determinant of a 3 by 3 matrix, if I'm allowed to not use a cofactor expansion. But we love cofactor expansion. Let's do this one more time. The stray marks are hanging out with us today, but we got it. And then I rewrite the first column at the end. I rewrite the second column after that, and that's all I have to do. Only for a 3 by 3. Let's get those downward products. So start at the upper left. Remember the word search. 2 times 1 times -1 gives me -2. Keep going, finding more diagonal products downward. -4 times 2 times 1 is going to give me -8. We can do one more of those. 3 times 3 times 4. 9 times 4 gives me 36. Let's get the upward diagonal products now. Start at the bottom left. Circle upward diagonally. 1 times 1 times 3 gives me 3. 4 times 2 times 2, that's 4 times 4, gives me 16. And -1 times 3 times -4, so it's going to be positive overall, positive 12. And remember, we add the downward, subtract the upward. So the downward products, I add them up. So that's -2 plus -8 plus 36. Subtract the upward one. So then I'm going to do -3, -16, -12. Let's see what we get. So here, let me go ahead and sort of jump around a bit, not literally, but with my arithmetic. -2 plus -8 is -10, plus 36. Let me put the -16 next. -3 minus 12, sure. So let me go ahead and do, this looks like nice arithmetic. 36 minus 16 gives me 20. I like -10 and 20, because I know this is going to give me positive 10. I like 10 minus 12 next is -2 minus 3 gives me -5 for that final answer. Just another way to find determinants of 3 by 3s. It's kind of cool. Show your friends, show your parents. Let's talk about one last thing before we end the lecture for this section. Let's talk about how the different elementary row operations are going to affect the determinant of a matrix. And I think you're going to be pleasantly surprised with what happens here. So let's start with this matrix A, and we can find the determinant of A. We know that's, so we just have A, B, C, D for the rows. That's going to be A times D minus B times C. But let's talk about row interchange. If I switch the rows, let me produce a new matrix, call it B. Let me switch the rows. So the first row is going to be CD, second row is going to be AB. Let's find the determinant of this. Well, the determinant of matrix B is going to be C times B minus D times A. Or I did the C times B minus D times A. Whoops, you saw that. C times B minus D times A. And I want to try to relate this back to the determinant that I got for matrix A. Okay, well, so what could I do with this is I could actually bring out a minus sign. If I factor a minus sign out, I'm left with negative CB and then plus DA. If I distribute back through, it gives me what I had before. So I can say, well, this is negative, and then if I want to just rearrange this, I'll write this first. This is DA minus CB. And it's really the same, because the order that we multiply doesn't matter. D times A is the same as A times D. C times B is the same as B times C. So if I notice, this is just minus the determinant of A. So we get minus the determinant of A. So when I do a row interchange, I really get the same determinant in magnitude, but the sign is different. The sign is off. Kind of cool. Kind of cool. Let's take a look at producing a new matrix. Let's call it C. We'll get a different color. What do we like? Let's do the red. Matrix C, where I scale a row. So the first row is AB. Let's scale the second row. So instead of CD, we'll do some number K times C, that same number K times D. Just imagine multiplying the row through by some non-zero constant. So we'll say K not equal to 0. And if I find the determinant now, I'm going to get A times K times D minus B times K times C. And here what I can do is I can sort of, rewrite this. Let me bring the K's to the front. That's K times A times D minus K times B times C. And I can actually factor K out since it appears in both terms. That's K times, here we have AD minus BC. Now that should look familiar. In fact, AD minus BC was the determinant of A, and I have K times that. So this is K times the determinant of A. And this was, so let me sort of make a note here, this was scaling. So just to refresh, when we did row interchange, the sign of the determinant flipped, though the number stayed the same, just the sign of it was different. When we did scaling, when I scaled a row by some non-zero constant, the determinant also got scaled by that same constant. Kind of cool. There's one more elementary row operation to look at. Let's do that. Let's get the pink. Let's take a look at a matrix D. Let's do row replacement. So here I'm going to keep that the top row AB, but in the second row, I'm going to replace that row with the sum of itself and the multiple of another row. So how would that look symbolically? Well, that would be, instead of C, it would be C plus K times A. And instead of D, it would be D plus K times B. I'm replacing the row CD with its sum of itself and the multiple of another row. So it's the multiple of row 1 added to row 2. Think of it that way. Well, what's the determinant of this going to give me? Glad you asked. It's going to be A times, in parentheses, D plus KB minus B times, in parentheses, C plus KA. And let's expand this out. If I distribute in, I get A times D plus A times K times B, and then minus B times C, bring that minus sign in as well, and then minus B times K times A. But we're going to get some stuff to cancel. A times K times B and minus, this is B times K times A, but it's really the same product, right? A times K times B, but I'm subtracting it. That's going to cancel. These two are going to give me 0. So I'm left with A times D minus B times C, which, this is interesting. What was that? That was the determinant of the original matrix A. So this is equal to the determinant of A. So what did we find out? Sort of recap here. If I have a matrix that I'm starting with, and I know its determinant, if I interchange two rows, I'm flipping the sign of the determinant every time I do that. When I scale a row by some non-zero constant, I'm scaling the determinant by that same constant. Row replacement, interestingly enough, was safe in the idea that it did not change the determinant of that matrix at all. And that's something I'm going to want you to definitely remember for the next couple sections. But hey, I hope you had a good time. I hope you enjoyed this conversation about determinants and introduction for us. No matter where you are, make sure that you keep learning, keep dreaming, and always follow your heart. I'm not going anywhere. I'll be doing more stuff with math soon. But until then, take care of yourself, and I will see you next time.